Welcome to the explainer. We hear the phrase the cloud tossed around constantly, right? It makes computing sound weightless, invisible, almost like magic. But the reality is actually the complete opposite. Today, we're going to move way past that abstract idea and actually trace the literal physical journey of the heat generated by a single AI prompt. We're looking at the massive, localized, super physical infrastructure that actually makes artificial intelligence tick. All right. Here's our roadmap for today. We'll start with the prompt's physical form, see how heat crosses the boundary, follow the evaporative exit routes, unpack the water-energy trade-off, explore exactly why water is local, and finally, look at the operator's balancing act. So let's jump right into section 1, the prompt's physical form. We start at the origin of the heat, the very millisecond you hit send. Picture this. You're sitting at your desk, you type a simple command, say, summarize this 50-page document, and you hit enter. Boom. We send these simple, supposedly weightless text commands every single day without a second thought. But instantly, that action crashes into a massive physical reality. The moment your prompt hits a data center, it demands computational power. And computational power? Well, that demands raw electrical power. It's an immediate conversion of your request into physical energy. To really put this scale into perspective, the empirical data from the Berkeley lab is staggering. To process today's complex AI models, data centers use these massive specialized accelerators, like 8 GPU servers. During heavy computationally saturated training, just one of these server nodes can draw around 7.9 kilowatts of power. And those maximum ratings? They're climbing toward 11 kilowatts and beyond. And here's the absolute fundamental law of computing you have to remember. Every single watt of that electricity instantly becomes physical heat. Which brings us right to section 2. Heat crosses the boundary. Because heat is never destroyed, it just moves. Let's trace how operators actually capture and manage it. So what we're looking at here is a crucial physical baton pass. As the silicon chips process your prompt and heat up, that thermal energy has to go somewhere, or else the whole server would literally melt down. First, the heat moves from that blazing hot chip into a liquid-cooled loop right there at the server rack. Liquid is incredibly efficient at absorbing heat, so it's perfect for this. Next, that hot liquid travels to a coolant distribution unit, or CDU. Think of the CDU as the ultimate heat exchanger. It takes that thermal baton from the highly controlled IT water loop and passes it over to the facility's larger condenser water loop. The genius part? It transmits the heat energy while keeping the two water systems completely physically isolated. They never actually mix. Now we follow that heat outside in section 3, the evaporative exit route. The heat is in the facility's condenser water loop, so let's see how it finally escapes the building. How does it get out? Well, it gets pumped to massive open cooling towers, where that warm condenser water is exposed to the outside air. Through a totally natural combination of heat and mass transfer, a small portion of that water actually absorbs the IT waste heat, changes from a liquid to a vapor, and evaporates. As it floats up and escapes into the atmosphere, it carries your prompt's heat right away with it. But here's a fascinating hidden consequence to all that evaporation. When that water turns to vapor and leaves the tower, naturally occurring dissolved minerals, stuff like calcium and magnesium, get left behind. It's kind of like boiling a pot of hard water dry. As more water evaporates, the mineral concentration in the remaining water spikes. If they aren't careful, this causes massive scale and corrosion inside the facility's pipes. To prevent that, operators have to actively flush out a portion of this highly concentrated mineral water straight down a drain. In the industry, they call this process blowdown. And that brings us to the actual mass transfer equation that dictates exactly how much water a facility really consumes. The Department of Energy lays out that a facility must add fresh makeup water to replace everything that gets lost. So makeup water equals the water lost to evaporation, plus the blowdown we just talked about, plus a tiny bit of drift, which is really just those microscopic mist droplets you might see escaping the top of the tower. Now, water is precious. To save it, operators try to maximize what they call cycles of concentration. That basically means safely reusing the recirculating water as many times as humanly possible before finally blowing it down. Minimizing the fresh makeup water they have to constantly pull from the local utility. And that perfectly sets up section 4, the water-energy trade-off. This is the inescapable choice at the heart of thermal management. Do you use water or do you use electricity? It creates this fascinating push and pull, and honestly, the conversation around it often gets way oversimplified. We have site WE, that's the direct water consumed right there on site by the evaporative coolant towers, but then we have source WE, the upstream water consumed by power plants just to generate electricity. Let's say you decide to use a dry, air-cooled system to save direct site water. Well, now your chillers have to work so much harder, the system runs hotter, and it uses a massive amount of extra electricity. But here's the kicker. Generating that extra electricity often consumes vast amounts of water upstream at the power plant. So reducing direct site water can actually increase the overall source water used. There are completely complementary metrics, not competing ones. This complex reality leads us perfectly into Section 5, why water is local. Because of this wild trade-off, trying to assign a single universal water cost to one AI prompt is virtually impossible. Just look at how many local variables drastically change the math. An evaporative cooler sitting in a super dry climate is going to act completely differently than one in a humid climate with a high ambient wet bulb temperature. And your upstream water footprint? That depends entirely on whether the local power grid is running on solar, wind, or really thirsty fossil fuels. It depends on local water quality, watershed stress, and how many cycles of concentration the specific pipes can even handle. The equation literally changes everywhere you go. Plus, we absolutely have to acknowledge the physical failure boundaries of these systems. This isn't just theoretical math drawn on a whiteboard. Operators face constant real-world threats. Extreme heat waves and high humidity events can render evaporative cooling totally useless. Sudden municipal water restrictions might force a facility to completely stop using site water. Operators are constantly battling mineral scaling, biological fouling in the towers, and, of course, the ever-present terrifying danger of liquid loop leaks sitting right next to million-dollar electronics. If any of these systems fail, it leads to immediate thermal throttling, where the servers choke themselves down to survive. Or worse, a complete facility shutdown. Which brings us to our final section, the operator's balancing act. You see, data center operators aren't just sitting in a dark room wasting resources. They're conducting a highly complex physical symphony. They aren't looking at just one variable. They're monitoring a massive dashboard of competing constraints. Think about it. Turning the dial to save site water might completely spike your energy and carbon footprint. On the flip side, lowering your energy footprint might require running your equipment hotter, which threatens reliability during extreme weather. Operators are essentially walking a tightrope, constantly having to balance uptime, capacity, cost, and the very specific environment of their local watershed and power grid. To wrap up our explainer today, I want to leave you with a really crucial local systems engineering question. If shifting away from on-site water usage ends up pushing the strain onto our power grids, how should your local community balance its own water energy resilience equation? Because when it comes to the immense physical infrastructure supporting the AI we use every single day, there are no perfect universal solutions. There are only highly localized trade-offs. Thanks so much for joining me to trace the heat, and I highly encourage you to take a look at your own local grid and watershed to see exactly how this balance plays out right in your backyard.